So it's my pleasure to introduce Joel Burdick, who's here from Calif. So I have the official blurb on where Joel did his undergraduate and his master's and PhD, and you guys all got it by email. Yeah. Instead, what I'm going to do is I was a graduate student when Joel was a professor at Calif. I'm still a professor, and he's still and he always had the coolest toys. He always had the snake robots and the things running around on the rugged terrain and just the coolest stuff. And I think you kind of still do. And so it'd be nice to hear about some fraction of that stuff in the next hour. Thanks, Ben.
As Ben said, I'm an old robot guy, and I still do robotics. But starting about 12 years ago, this guy, Rick Anderson, a neuroscientist at Caltech, called me up one day and said, do you want to hook a monkey's brain up to a robot arm? And I said, great, count me in. So I worked with him for about a decade on developing a new technology to kind of go into cortex. And originally my plan for the talk today, I was thinking about splitting the talk between these two. But rather than rushing through it, and because we have some interesting new results on our first human studies in this area, I'm going to pretty much spend the whole talk on this. And so I want to stress a couple of things. So thing number one to stress is this is a collaborative effort. I'm just the messenger for a big team. This isn't all my work. I'll try to identify the things I contributed to, but there's a lot of great collaborators. Reggie Anderson at UCLA, Susan Hartman. Reggie spent almost 40 years of his life on spinal cord injury. Susie spent 20-some years of her life on this. Yuri Gerasimenko, many of you don't know him. He runs the Pavlov Institute, the neuroscience program in St. Petersburg, Russia. This is the Pavlov of Pavlov's dog. And he's a real character. And if you want to know the best vodka to drink, he's the man to talk to. I didn't necessarily go into this field thinking of doing this, but what sort of emerged out of my activity here as an engineer is trying to engineer adaptive interfaces to the nervous system. And hopefully I'll try to get this across to you. And by adaptive, there's many different issues, both overcoming for implant errors, overcoming for shifts of the implant technology over time, overcoming the fact that people's pathologies are different, and overcoming the fact that the nervous system actually changes over time, and one needs to adapt to that. So I can't say we've handled all these issues, but we're trying to develop that. And so the other thing is, Ben said, you have to have a talk that has to have robots, micro devices, bioengineering, and algorithms in it. And so I promise you all of those, plus humans and rats on top of it. Since it's a broad audience, I hope you don't mind if what I first do is just give some broad definitions. Let's set the context here. So as we all know, when the nervous system has either damage or disease or something, one loses a certain amount of function, sometimes a terrific amount of function. And Avis is going to kick me in the shins, because the last time I showed this slide to her 3 years ago, she complained about the word neuromodulation. So Avis, I'm sorry, I stuck with the word. And in the bio-device community, not necessarily the neuroscience community, we're going to use the word neuromodulation to mean coming up with a device which either is going to modify the nervous system, augment it, bypass it, interface to it, or some way manipulate the nervous system. And neuromodulation is it's a real industry. Actually, it's a multi-billion-dollar-a-year industry. And so if those of you haven't seen it, many of you know about the cochlear implant. And so people here at Maryland, as well as many places around the country, have worked on cochlear implants. This is now a successful technology. Over 100,000 of these have been implanted worldwide. And even though they only interface to about 8 to 16 neurons, and these are typically for elderly people whose nerves can still transduce the sound, but the hair cells are degenerated, so they actually can't do the mechanical transduction. Even with that small number of interfacing to the remaining audio system there, they can hear about 30% of speech and recover reasonable amounts of interaction with the outside. So much less developed, but now in serious clinical trials, is the use of not inputting to the audio system, but the visual system. And so not necessarily aimed at people who have been blind since birth, but for people who typically who lose sight as a combination of either a genetic disorder or as a byproduct of diabetes or other sort of age-related diseases. Their macula will degenerate over time, and sort of about 1 million of these people will suffer some very serious vision loss. And so there's been a few dozen people now implanted with these retinal prosthetics, as they're called, and so it's an emerging technology. So it's starting to work, and now they're really trying to advance it. So many of you may have seen this also. This is, instead of putting information into the system, there's a whole line of thought now of actually, again, trying to modify the system. And so for Parkinson's, A deep brain stimulator, as they're called, has been successfully used in over 50,000 people so far. By stimulating a certain area of the brain, it can actually affect nearby areas and affect the dopamine balance, dopamine production to sort of modify the Parkinson's cells. And so these are doubling every year now, the number of actually implanted. So it's a widely growing technology. To some extent, in my personal opinion, it's actually starting to get almost abused. Actually, a number of companies now are looking to use this for all kinds of things, like shopping addiction, gambling addiction, and other kinds of things. And it may be useful for those, but it might be stretching it a little bit too far. So this is going to play a role in my talk later today. People whose back pain can't be treated by surgery or drugs or physical therapy. One strategy is these electrode arrays are implanted in the epidural space. I'm going to talk about that more later today. And basically a stimulator pack, which is also implanted, applies electrical stimuli at a high frequency to not necessarily get rid of the pain, but basically mask the pain, so the patients feel a sort of paresthesia or tingling instead of a severe pain. And these, there's over 100,000 in the US, and these have been implanted, and they're going to play a role in our talk later today. The one that's interested me, and the one which is, in my opinion, less developed, are sort of motor deficits. We talked about getting information into the brain, modifying what's happening in the brain, and now we want to get information out of the brain for people who's lost motor function from a variety of conditions. So many of you may know Stephen Hawking, the sort of great black hole physicist. He's a late-stage Lou Gehrig's disease sufferer, and so he's now reached what's called a locked-in condition, in which he can see and hear and think like you and I, but he's lost almost all ability to control any motor movements except for maybe his eyes. And so this is actually where I got started with Richard Anderson, but I've sort of shifted over in the last 8 years to really working on spinal cord injuries. And one of the reasons is that in terms of the motor deficits, this is sort of one of the larger populations in the US. So there's at least 250,000, and depending on how you count, maybe more people with very severe spinal cord injury, and about 11,000 new cases per year. 50% of these are what are called complete injuries. We're going to use the word complete to mean that actually below the level of the damage, there's actually sort of no motor function. So we'll say motor complete, there's no motor function. Sensory complete means there's no sensory function, and motor and sensory complete, obviously, for both of them. The thing which is different about spinal cord than the other diseases, not diseases, but conditions that I talked about, is that this is typically an injury of youth. The median age in the United States for injury is 28, so most of you students out here, you're in the prime stage of life for spinal cord injury. And I don't actually have the statistics here. Actually, no, I'm sorry, I do. So the majority of injuries basically call from motor accidents, violence, and sports. Those are the major ones in youth. There's the falls go mainly in the elderly. Okay, so now this is really embarrassing. I have to actually describe neuroscience in front of Avis Cohen, and so Avis, be kind. So I'm giving you a really rude layman's view of sort of spinal cord injuries here. And so here on the left, there's the complete spine from the cervical area down through the thoracic, all the way down to the lumbar sacral area. And so when you want to move your lower legs, there's sort of 3 basic systems that you can actually use to move your lower limbs. And you know, most of you know about 2 of them. People like Avis have pioneered the 3rd one that we'll talk about in a moment. And so when you're doing something very athletic, you have not a direct connection between your cortex and your muscles down there, but you have relatively direct pathways so that you can exercise fine control for doing athletic sports. Now obviously in a major spinal cord injury, these pathways are gone. There's actually a secondary effect that we'll talk about a little bit also, is in addition, some of the key neurotransmitters, the monoamines, norepinephrine, dopamine, especially serotonin, which will play a big role in our talk today. What's that? Yeah, the neuromodulators. I call them the monoamines. That includes histamine too, which we don't care about. So they're actually synthesized largely in loci in the brain and sort of transported and made available through long axonal projections. After a major spinal cord injury, this transport process is stopped, and these particular neurons largely wither away and die. So a third pathway, which is the least important for today, but let's just get out of the way, that you all know about are sort of fast sensory reflexes. So you step on something hot, and even before the signal gets to your brain, there's already an interneuron, or not interneuron, there's a direct synaptic connection, which returns to a motor neuron, which gets your legs moving so that you don't hurt yourself. And after a spinal cord injury, these are actually intact, and actually will stay intact for decades, although their function and ability will change over time. The one that's going to play the central role for us today is, again, that area that Avis is famous for, and that's why I'm embarrassed to talk about it in front of her, is what we'll call a central pattern generator. And so as you're walking down the hallway and thinking about the homework exam or the movie you saw last night, there's a lot of sort of local feedback circuitry in your lower spinal cord, which takes care of sort of generating the rhythmic motions and actually doing a fair amount of feedback control, taking sensory information from your muscle spindles, also from sensors on your skin and your joints, etc., and using modulation from the cortex to sort of set the guidance and the goals for what the central pattern generator will do, and then it sort of executes a lot of the low-level details. Now, obviously, in a major spinal cord injury, the modulation and the sort of starting and stopping by the brain is cut off. But the thing which is useful to us is this central pattern generator circuitry. Now, in lower vertebrates like the lampreys and in invertebrates, we actually know where this circuitry is. In the human spinal cord, we believe it's here because all the evidence says it's here, but we actually don't know which specific neurons are involved in the CPG. But it has CPG-like behavior. And I'm using the word CPG broadly because not only for stepping motions, but all the sort of major posture control circuitry is down here. Obviously, you use vestibular and ocular sort of input to control your balance, but there's actually quite a bit of circuitry down here. And the amazing thing is this circuitry, again, does not degenerate. These circuits will stay around for decades, although their function will degrade over time. And so our goal then is to, as engineers, is to try to tap into the circuitry. Right? So this is a relatively modest goal. We're not actually trying to bridge the gap to the brain yet, although that's a longer term goal we'll talk about at the end of the talk. But right now what we'd like to do is sort of tap into the circuitry, get the most use we can out of it, provide some benefit to patients, and also move us towards the day when either we can think about an engineering bridge across this, or the stem cell people, or tissue regeneration people, or the tissue scaffolding people, or all the different approaches being worked on can bridge that gap for us. Because even if they can bridge that gap, it's very naive to think that actually after a major injury, you're going to go in, snip out the cord, inject some stem cells, and get up and walk away. It's just not going to happen. And so the technology that I'm going to tell you about today is also going to be useful for that sort of future as well. Okay, so this is work with my collaborator, Reggie Edgerton. I didn't do these experiments, although I was working with Reggie at the time. And in some sense, this should come later. But what I want to convince you of here is that actually the central pattern generator actually does have a lot of feedback circuitry in it. So this is actually a rat. It's a Sprague dolly rat. And its spinal cord has been completely transected. In fact, even plastic put between the two ends, so there's actually no neural reconnection whatsoever. So using the techniques I'm going to talk about today, epidural stimulation is not new, it's an old, but we have some new twists on the kind of electrodes we're developing, spinal stimulation, plus drug therapy that we'll talk about today, plus physical training, happens to be robots in this case, and that's partially why I'm involved. So this is an animal. Now, at this stage, the animal cannot bear its full weight. So you're going to see these rats walking in a funny way because we're helping them to support their weight. They can't yet bear their weight. But to show you that actually you don't really need the brain to actually get quite a bit of locomotion. So this is a rat. Again, his spinal cord's been completely transected and disassociated from his brain, but with the stimulation and drugs and therapy. And so going forward. So this isn't so surprising, but if you actually reverse the treadmill, it'll start stepping backwards. And again, there's no brain connection here. This is all just through the local feedback circuits down in the bottom of the cord there. So there really is something there we can take advantage of. And this is one of the most amazing ones, is actually they'll step sideways. All that circuitry is in there. It's not done by the brain. The brain can modulate it, the brain can improve it, and all kinds of things. But the circuitry's there. And so one of the things which we didn't know at the beginning of our study is these kinds of ideas have been known for a long time. Reggie's been one of the leaders in promoting them. Would they actually work in a human? And so I'm going to get to that later today. But what I want to do first is kind of, in some sense, tell you a chronological story of sort of how we got to where we are today, and sort of my own personal work as well as part of this team. So with my brief review of the physiology of spinal cord, what I want to emphasize is that the circuitry below the spinal cord is intact and plastic, which means it can readapt and we can retrain it. So we can therefore try to engineer it to help the people as much as we can at this point. A key thing, and this is one of Reggie's great contributions to the science, is sort of showing that for this circuitry to work, it actually is dependent upon getting sensory input from all the muscles and all the skin sensors and joint sensors to really activate that circuitry, even in its natural state, much less its damaged state. And that one of the problems we have to deal with then in trying to rehabilitate this lower cord is deal with this altered chemistry that I sort of mentioned. And also through Susie Hartmer's work, one of our other collaborators, she's been a leader of sort of showing physical training can actually sort of readapt these things. So by physical training, drugs, and also new technology, what we want to do is tap into the cord. So in some sense, this slide is already moved. I've sort of basically said that. So I'm a robot guy, so part of what we do in the animal models is develop robotic devices to administer the training. And we'll talk about that a little bit. We use drugs. I'm not going to spend too much time on that. So the key thing I'm just going to say right now is that for motor learning, that is learning new motor pathways or new motor connections, serotonin is one of the most, it's not the only, but one of the most important drugs. So our group tends to focus on using a variety of serotonin-related drugs as part of the therapy. And then a lot of the talk is going to talk about epidural stimulation and sort of new technologies that we're developing to do that. Okay, so what I want to do is build it up. So let's say, okay, without any fancy electronics or fancy stimulation, what can we actually just do with good old physical training and some drugs? And so this is a series of work I did with Reggie, led by my students about 6-7 years ago now. And what we asked the question was, if we have, again, a completely transected mouse, how long would it take to basically retrain that lower spinal cord, that CPG, if we applied it with the right sort of pharmacology so it can actually relearn things? And so this is the same animal over a series of first 1 week after the spinal cord transection and daily dosage of drugs and daily stimulation and daily, not stimulation, daily training, 4 weeks and 6 weeks. Now, this little robot here, let me sort of show it in the previous picture. This is a schematic diagram of it. Each of these limbs here has 2 motors, and this attaches the ankle. So we can use this robot in 2 ways. We can either drive the legs through a pattern via training, or we engineered this so that the mass and friction is so low that even these paralyzed mice can actually move the limbs by themselves. So we can use it as a measurement device to see actually how well we're recovering. What's that? This in particular, at this time we were doing mice. This is earlier. We switched to rats. Man, rats are tough. You can't kill a rat. That's right. Yeah, exactly. And so it just physically, they're just much easier to work with. Yeah, question?
So you're removing visual input by putting the socket in your head?
And the reason we're doing it is because the mice get scared. And so, or sometimes, not all mice, some of them actually just get agitated and fidgety, and so we wanted to remove that. Not because of any sort of sensory pathway or anything else, it's just strictly for the comfort of the animal. Like putting blinders on, of course. Okay. So here's what happens in 1 week, and so what's down here is you see the visual sort of performance, and up here is the sort of path that the animal traces out its ankle in doing it. And what you see is, after 1 week of training, there's a little bit of function, but sort of not much is happening. So it's kind of, pretty close to just being spastic activity. So if you do this every day, so 20 minutes of training a day, plus you have to inject this drug. It has a short half-life, Pasadena. It's a serotonin agonist. It basically serves as a replacement for serotonin. So after 4 weeks, you actually kind of see some reasonable kind of stepping starting to emerge. And actually after 6 weeks, you actually see quite nice stepping research training. And what I want to emphasize is this animal is not yet supporting its full weight. And there's, again, the brain's totally disconnected, so we've basically just done this cheesy thing of building in a new reflex. So we just basically repattern the reflex so we can use the spinal cord to do things. Now, we're not the only teams who have done this. This is sort of doing this in a robotic model, and also this particular drug is showing that this is sort of very effective. So one of the early questions we asked was, okay, if you're going to do this kind of work, what's the optimal way to try to rehabilitate the spinal cord? And so one of the things you want to know is sort of what's the fundamental mechanism of the recovery or the plasticity underlying that recovery with robotic or physical training. And maybe Avis has better ideas than I do, but it's my understanding that that's not completely known right now. And so we sort of undertook initially a sort of empirical study. And obviously, one of the reasons robotics is interesting, this is called Locomat. This is developed over in Switzerland. This is a commercialized device which came out of ETH Zurich, I believe. Because physical training of these spinal cord patients is very expensive. So this is a training therapy of a person who's a young 25-year-old male in a car accident who suffered a complete spinal cord injury. And sometimes with very intensive training over periods of months and weeks, they can recover some locomotion, so you don't know until you try. But to actually go ahead and carry out this therapy, you need actually 3 therapists. Actually, you need 6 therapies. Because 3 therapists are both moving his legs, trying to put the pattern in, and also guiding the hips. And after 20 minutes, they're so exhausted, another team has to come in and sort of do that, because it's very labor intensive and very expensive, as you can imagine. And so the people who've been developing robotic devices are sort of saying, well, if we can actually automate that, that would lower the cost and therefore allow us to extend the benefit to more patients.
You also have to continue the duration of the cycle.
Yeah. And what we do know, and actually I'm going to talk about it later today, is you see actually recovery for years after the injury if you provide continued therapy. And the problem is insurance companies won't do it.
You have to provide continuous therapy.
Yep. And so what we want to do is make it cost effective so that insurance companies can't say no, don't do it. Yeah. Because right now they don't provide 3 months. That's it. And so what's been known in the neuroscience literature for decades is that even when you take a healthy animal, so this is actually a completely intact healthy mouse on our little robot, this is the path that the ankle follows during a normal trajectory, and you see sort of a large variation. So variation is a natural part of sort of biological locomotion. The other thing is actually some of the early studies in the locomat actually sort of showed that they actually put people on the locomat and they just sort of moved their legs through what they thought was a useful training exercise. And over time, they actually got less and less muscle activity. And so it's kind of like habituation, and it's also being called learned helplessness. So that the idea is that the nervous system basically learns to tune out that sort of constant thing. So we also know you wanted some variation to sort of continually challenge the spinal cord. And what you saw in the therapists before is that actually if you look very carefully, and if you sit there and watch these really trained therapists, you say, oh, anyone could do this, but then you watch very carefully. What they do is they know exactly where to hit the knee to give a little sort of sensory input, and sort of which muscle to slightly tickle to get the right sort of spindle fiber to really generate. And these people are very trained. And the key thing that they've told us is that the best strategy is to use an assist as needed idea, which is when the patient's doing okay, let them go. But when they need help, then give them just the bare minimum help they need. So we wanted to see, could we build this into a robot? So I took a group of mice and sort of split them into sort of 3 different groups. And so the first group, we sort of followed what was then the kind of traditional locomat paradigm of sort of moving the ankle through a very fixed trajectory. The trajectory we chose is actually not from a healthy animal, it's called from a neonatal mouse. So these are mice which are transected at birth. So this is sort of, and they sort of get partial recovery of stepping. And so this is, in some sense, a natural motor pathway for an injured animal. And then what we also sort of said is, well, one way to interpret the assistance needed is what the therapists are doing is, if you're close to the path, then don't do anything. And if you're outside the path, then actually bring them back into a region sort of near the desired path. So we call this the band method. And so the way we implement this is with sort of a series of vector fields or force feedback vector fields. So all through space where the animal's ankle is, this is sort of the response that we give from the robot to do that. But this actually has then no coordination between the left and the right legs. And so we added a third study group, which what they did then is we had sort of a moving window, which is if the leg was roughly on time and roughly in the right location, leave it alone. But if it gets way behind schedule or way ahead of schedule or way out of the zone, knock it back. And so rather than show you a bunch of data, I'll just show you some video. And so recall that a second ago I said you could use this robot in both training as well as sensing mode. This is in training mode. So this is the locomat style idea where it's just sort of using a fixed pattern day after day after day. This is after 6 weeks of training. It's hard for you to sort of see, but partly because the video is so bad, I apologize. But you'll notice its toes are dragging. It's actually not getting the sensory input that it needs to sort of recover well. The amusing one is the next one with a band, where what we necessarily, again, the left and right legs are getting the sort of assistance needed, but there's no sort of coordination between the left and the right. And so what you see this animal doing is that the left and right patterns are actually quite good, but they're not phased. They just go out of phase, so they didn't learn the phasing. And so what we do know, there's actually a bunch of sort of interspinal pathways down there that also need to be properly retuned if we're trying to do this there. And the most interesting one then is of course, the champion was the sort of do both phasing as well as sort of the proper shaping of the thing. And so again, this is training, but this kind of shows you they get the proper placement of the feet, etc. And so this was fine, and so this was sort of starting to build up a repertoire of the technologies we want to apply to kind of spinal cord injury. I'm going to pass that. But
Would the rat walk on its own, or only, I mean, if it was in a walker, if it wanted to walk, if there was no treadmill underneath it, or is this only triggered by the treadmill?
it's only triggered by the treadmill. You can get it to work non-treadmill if you jack up the glucosine, which we don't want to do, we don't do. It will reach a level where it actually excite the CPGO and actually get what is called fictive stepping. But it requires a very high dosage of glucosine, and we don't use that dosage. So we try to do it so that it facilitates, but not open loop generate fictive stepping, but actually requires a sensory input from the device to get it started. And what's nice about it is actually you can actually speed up and slow down the conveyor belt by a factor of 3, and the animal will actually just adapt to it if you train it properly.
So what do they do in their home cage? Do they just sit in one corner, or do they actually try to drag themselves around?
They drag themselves around because we do a mid-thoracic, so their front legs are perfectly fine, and so they learn very quickly just to sort of drag themselves around.
You don't have to help them feed.
No, you have to help them feed, but this is the worst part of it, and unfortunately grad students do, not me. You actually have to express their bowel and their bladder, and you have to do all kinds of things that don't get infection.
Joe, I have a quick question.
Yeah.
So, well, I didn't catch this, but the feet were actually connected to those linkages, right?
Yes.
But those linkages are not actively controlled?
No, I can use them either in active mode. So the second set of videos, they were in active mode. It was training mode.
Right.
The first set of videos were in measurement mode, where there was no current provided to them. It was measurement mode.
And how do you phase that motion with the treadmill?
Oh, they're all connected to the same computer, and so we can. And so what you do is we know the stepping rate, and so we can then just set the treadmill speed based on the stepping rate. During the training, but during the measurement, we just turn this to treadmill on different rates, but we actually don't. Then the arms don't move, and so it's up to the animal to make the adaptation. Okay. So this sort of says, yeah, the CPG could be a potential tool if you train it and you give it drugs. You can do some pretty wonderful things with it, but it's not enough really for clinical use. All right. So now the question is, what do we do next to sort of tap into the lower spinal cord? So this has been the micro devices part of the talk. And so at that time, I was working with Yu-Chang Tai, who's a terrific micro-machining engineer at Caltech, on another project. And so one of the things he's been working on for many years is retinal prosthetics that I talked about in the beginning. And so he was working on some technology, and I looked at it and said, you know what, we can think of the spine of the retina. And Yu-Chang, why don't we adapt your technology to the spine? So this is with my student Andy Fong and two of his students and I, we came up with this sort of first generation design. And so this is how this thing is built using silicon micromachining technology. There's a 20 micron layer of paraline here. It's actually laid down in multiple layers. On the paraline, we then deposit either platinum, gold, or tungsten, most of the time platinum, both wire traces and electrodes. This is a mice scaled one. And so this one is sort of scaled at 2 millimeters across for the mouse spinal cord. Each of these electrodes is 250 microns across, and each of the inter-electrode spacing is set so that we actually get up one intervertebral segment of the mouse spinal cord in this sort of first design. I'm going to come back to that later. And so we then use what's called an epidural placement. And so for the engineers, the dura is a thick sheath all around your central nervous system, prevents infections from going in there. You could go intraspinally. Other people do that. There's some really intraspinal work. We've chosen not to do that because it's not necessarily safe for human patients. And also, if you're successful, the spine's really moving. And so if you have a rigid electrode in that spine, you're probably going to do a lot of tissue damage. And so it's going to require a whole other generation of technology to do that. And so we've been sticking with the epidural space. So nature gave you in your vertebral canal a little bit of space between your spinal cord and the interior wall of the vertebra, so that when you bend, you don't pinch your cord. And it sort of fills that space with a little bit of fat. So what we do is a laminectomy. This is both for rats and for the humans that we'll see a little bit later. We basically pop off half of the vertebra. Then we tie a suture to the front end of this array. And we basically thread it down through the vertebra. Then we pop off another vertebra down the bottom, and we just pull it. And then it's sort of sitting there. It just sort of sits there right on top of the dura, as close as you can get. So then the wire traces are brought off, and so for the most part now it's still wire bundles coming out, but we're reducing the number of wires and we're getting close to wireless at this point. And so in this early work, what we showed then is by stimulating both different voltages in different electrode arrays and also different combinations of electrodes, what we could do is get, in some cases, individual muscle group control. A lot of times what we can get is sort of coordination motion across muscle groups. There are a lot of sort of interspinal connections and interneurons in there, and so we tend to hit up many of them and get a kind of combined response. But we found that we could actually then sort of meter, we could actually linearly kind of control the response based both on the spacing and the voltage level of the electrode. So we convinced the government to allow us to then go on and develop more advanced technology and also do a human study that I'll start talking about in a moment. And so this is the next generation of arrays that we developed. And so in order to get more fine control over the spinal cord, These arrays, if you look up closely, in each vertebral segment actually have a central electrode array and then a left and right electrode, so that you could get asymmetry in the stimulation patterns. And we now, in this generation, we also moved up to rats. And so this is much bigger and much easier to deal with. In this generation of technology, we have tons of problems. And so because we have 27 electrodes altogether, 9 vertebral segments, plus 3 electrodes per segment, plus we implant all the EMG electrodes, we can actually monitor all the main locomotory muscles and get evidence of whether we're succeeding or not. And so it ends up being, by the time you're done with power and ground, almost 72 connections coming out of the head. And the rats didn't like that. And we also had a high infection rate and a high failure rate because of this. And so more recently, we've been able to succeed. And this is now a system where, using commercial chip technology, this is basically a board, a multiplexer board, where we get the 72 wires down to 12 wires. And now Monty Nandra, the key graduate student working on this in Ty's group, has been, at least in the lab, demonstrating wireless connection. And so we're moving towards that. And many groups will move towards wireless. This isn't particularly novel, but it's just a hard challenge. And so where we apply this, Avis, to get back to your question, is we put now the 9 lowest vertebrae starting at L4 going up the spinal cord. Now remember, rats have slightly more spinal levels than humans do. And so we actually get up right to the bottom of the thoracic level. Most of our spinal transections are at T6. And that's where we do it.
But you're just stimulating the lumbar segment.
With the lumbar sacral segments.
And it's only dorsal root?
What's that?
It's only dorsal root stimulation?
No, well, so I'm going to come back to that in more detail later, but we do have these 3 electrodes across, and so we can both do sort of bipolar pairs, we get gradients left and right. We can actually do the outer ones if you want to get dorsal roots. You hit the nail on the head. Actually, hypothesis that I'm going to confirm a little bit later with the computational study is actually dorsal roots are heavily modulated by this. It's clearly an important factor, but we're increasingly believing it's not the main, I should say the main factor, it's not the only factor. So we seem to be influencing other things like that.
The transection though is complete.
The transection is complete. In fact, it's not only complete, we actually put gel film between them so there's actually no regrowth. And whenever we finish the study, we always confirm that actually there's no regrowth between the spinal cord sections. Okay, now let's put it all together. So this is, again, now moving to rats. If you now take a rat and sort of transect it, and you sort of put it on the treadmill. So this is a healthy rat here before the transection. So here you can see its left and right ankle movements. So, healthy, normal movements. You transect the rat, and a week later, you put it on the treadmill, and it just hangs there. It doesn't do anything. You start to give it some drugs, and you start to sort of help modulate the CPG and also allow the sensory networks to start operating. And then you actually add stimulation. In this early study, it was only just very simple stimulation at sort of 2 levels. I'm going to talk about later more what we're working on now. Yeah.
How do we do those?
Yeah. Okay. Yeah, I apologize. Because in the neuroscience community, this is obvious.
Okay.
Yeah. So what these are so we have cameras trained on the animals, and so we have key markers on each of the major hips, knees, ankles, toes. And so this is basically the trace of the leg, and this is both the left leg and the right leg over time. What's here is showing the time in which the legs are planted on the ground. What here are shown, and I'm sorry I don't have the measure here, is the different EMG activities. So we actually measure the electrical field coming off of the muscles by electrodes implanted in key areas of each of the muscles. So what I want to draw your attention to then is mainly the sort of stepping pattern, and here's sort of the ankle pattern. Okay, and so as you add the drugs and the stimulation, within 1 week you can start to see some recovery of locomotion. And so if you keep doing this then for 7 weeks, what you see then is you get pretty good recovery of normal stepping pattern. What's here on the right is an animal in which they had the stimulation and the drugs but no physical therapy. So it's really seen that the physical therapy is a key tool to sort of help retrain those spinal circuits to take advantage of the technology of the drugs.
Is the ankle going higher than normal?
And yes, sometimes you get that. Reggie would give you a better answer than I would. I don't know whether that's a training effect or whether it's just something about the particular injury that the animal suffered. Okay, we then convinced the government to allow us to implant 5 people. Our technology is not anywhere close to being ready for humans. It would be a travesty for us to put our technology in humans because it's not surviving that long yet. So, but as I mentioned, these back pain stimulators, so they actually implant electrodes in the epidural space in the spinal cord, so it's the same area we do. And they have all the technologies ready to do it. We just put it in a lower area of the spinal cord, and we use it at a much lower frequency. At the very high frequencies, it gives you the sensory masking effect. At the lower frequencies, we can then actually access different parts of the networks. So our first subject is now, it's not public, so I can use his name, Rob Summers. In working with these people, he's an amazing guy, and truly just astounding guy. What's that? He was the age of many of you students out there. So he was 21. A couple months before his injury, he was the pitcher on the NCAA Division I national champions. He was a tremendous athlete. And while he was bending over the trunk of his car one night, a car hopped the curve, hit him, pinned him between his car, hit and run, left him there. They ran away. He was on the ground for 8 hours until the mailman found him the next day. And it was probably only because of his incredible training that he survived that. And so he has what's called it's a very complex injury. So there's actually a damage along much of his cord. You can see a lot of breakage and damage here. So he presents as what's called a C7T1. So initially he actually didn't even have complete use of his hands. So as soon as he woke after the injury, he got a ball and started squeezing 8 hours a day, and sort of got his hands back. And so he has a very firm grip. And so he volunteered. He was our first volunteer. And so obviously, these kinds of things are like a control experiment. It's kind of hard to do control in this case. So we use each patient as their own control. And so before implanting him, he went through almost a year's worth of daily training to sort of make sure that there was really no vestigial response that we could actually elicit whatsoever from very intensive training. If we got it, great. But if we didn't, then let's try the epidural stimulation. So we implanted it with this electrode array from Medtronic. So this is the array that has 16 electrodes. You'll see a better picture on the next slide. And also you implant a battery pack, which has a wireless remote that allows you to change a few parameters, and also onboard computer and remote charging, so you can charge this wirelessly. What's that? I'm going to talk some about that. Yeah. So we implanted this right here and in the very lower part of the lumbosacral part of the cord, and we're lucky there is even though this electrode array is shorter than we want, because of the geometry of the cord, we actually cover about 4 or 5 levels of the spinal cord there, and they're all in kind of the locomotor levels, the locomotor areas. And so what can we do? This array, this technology has many limitations because it was designed first for back pain relief. And so what you can do is you can turn each electrode on or off. You can choose whether its voltage is positive or negative. But all the electrodes that are on have to have the same voltage, and all the electrodes which are on have to have the same frequency. It puts out a very simple sort of square wave light pulse like this. So it's actually pretty limited. But for back pain, it's fine, but for spinal cord, it's limited. So this is just kind of a schematic diagram of the different options you have for turning that electrode on. So this is Rob about 3 weeks after the surgery. So we let him sit for 2 weeks. So he'd been in a wheelchair for 2.5 years. We couldn't get anything out of him after a year's worth of therapy, and he sort of got up and standing in just in a few weeks. And so this is actually this picture's taken about 6 weeks after his surgery. And so just to kind of show you the idea that we're actually trying to facilitate these circuits rather than actually replace them or sort of stimulate them open loop without sort of their natural pattern. What you have here is as we turn the voltage up on the array, these are actually the LMGs from all of the key muscle groups which are necessary for posture. And so you see at low voltage, his legs can't generate any postural control or anything whatsoever. Once we get above the threshold, all of a sudden these circuitry starts to turn on, and at a very high threshold, they start functioning. You get too high, then basically the open loop, he's just shaken because you're now just jamming the muscles and you're causing them to operate without sort of their natural operation. So here's what we did when we first sort of actually started him with weight support. So he's partially suspended, and then we sort of slowly lower him onto his legs, and we sort of see the circuit start operating better and better as he gets more sensory input to this.
So it is a periodic stimulation.
We use different stimulations for different tasks, and so it's very task dependent. So for standing, it's typically 15 to 20 hertz. For stepping, at around 40 hertz is the best we've been able to find so far. Well, the problem is with the technology, we don't have the fineness of control in terms of the variable. So this is kind of a training session from the early days. So this is about 4 months after his surgery, just to sort of show you what one of these sessions are like. So right now they're ramping up the voltage, and so you're seeing the therapist there assisting him to make sure he doesn't fall. So now the voltage is high enough so that his circuits, postural circuits, are now sort of controlling themselves. He does need in these sessions sort of assistance here for some balance. He actually can stand for periods of time without any assistance whatsoever, but to train for long periods of time, he sort of likes to use this. So, so this has exceeded all our expectations, but then some amazing things happen. So one of the things that you may not realize until you work with paralyzed people is that actually, in addition to obviously the motor movements that they lose, they have all kinds of autonomic malfunctions. So the average person who's at a C7 level or above spends an hour and a half a day managing their bladder valve. And so Rob himself was actually on the catheter because he couldn't control his bladder, and it was on continual antibiotics to manage the bladder infections, etc. And that's what kills them eventually, many of them. And all of a sudden, in about 4 months, and especially up to around the 7th month, he actually started reporting he was getting his bladder control back. And then we don't know whether it's an exercise effect or probably an exercise effect. These guys have blood pressure regulation problems. It's called autonomic dysreflexia. His blood pressure became regular. He got off all his blood pressure medication. He regained bowel control. Another one that stunned me is that actually below the level of the lesion, it's high enough they actually can't control temperature, so he actually can't go out and heat. And he realized one day when he was actually at a pitching clinic in Florida out in 90-degree heat, he was out there for 5 hours. He said, hey, I'm not sweating. I mean, I'm sweating, I'm regulating. So he got his temperature regulation back. And then this is a funny story, so I want to, unfortunately, I have to stop this to play this video. I couldn't get the codec for this video, I apologize. So one day, every month, we do a very extensive testing on Rob. And so Rob just says as a joke to the Claudia and Jelly, who's right here, let's see if we can fool Susie. I'm going to move my tongue. And he did it. And he didn't even know he could do it. And all of a sudden, Susie's like, stop screwing around. This is serious. And so this is, they turned the camera on right after that. And so this is his first voluntary movements. And so he was able to, on verbal command, I'm going to show you the data in a second, show it on flute, was actually able to recover voluntary control of some of his legs. And we never expected this. This is not something that we had planned for. Yeah, I'm going to talk about this. Okay. So here is, we had a high-profile paper come out back in May in Lancet. And so here's the data from that paper. And so here, with no stimulation, while Rob is on his back, we ask him, move your legs, and nothing happens. And then we turn the stimulator on, and we say, to follow some, move your legs. So here's the command, and you can see the muscles responding exactly during the command period, sort of turning off. And then a little bit later, after almost a year after his surgery, he actually started to be able to lift his leg voluntarily and start stepping. Now it's very, most of you think this is pathetic, but for him it was an incredible experience. And so here he is during the stepping training. So stepping is not nearly as good as posture. So it takes a while for him to get warmed up. So now what you'll see is he'll actually then lift his leg forward. And so sometimes the therapists actually have to help position it so it doesn't overextend. So now, unfortunately, because of limitations of technology, we have to set the stimulator so you see his right leg is much better because we can only get one leg at a time working well because of the limitations in the technology. And so the stepping is not nearly as good. So he can't support his own weight. So we're supporting about 50% of his body weight to do this. But obviously, we were all excited. So this is, I don't have data to show you because this just happened 5 days ago. So 5 days ago, he reported to us that he can now move his toes without the stimulator on. And we haven't measured it, and so this is unconfirmed speculation. It's only a report from him. Let me stress that. But it's exciting. And so, what's the mechanism? I don't know. And so, everyone in this audience probably has a different idea. They're probably all as good as our ideas. So one is, in almost all spinal cord injuries, even if they're complete, it's pretty clear that there's probably some remnants of the cord there. And so these neurons can go silent for a variety of mechanisms. They may demyelinate because of the damage. They just may be traumatized after time with the stimulation.
The question will be whether you get it muscle, whether it's just certain muscles, suggesting that it is some kind of isolated fibers that are.
Yeah, we don't have the extensive studies yet. Another one, because of the time scale, it's possible, and it's well known that actually after spinal cord injuries, the body naturally, even though the central nervous system doesn't regenerate as much as the peripheral nervous system, the body actually does have some what we call aberrant neurite sprouting. And it may be by stimulating from below. It's known from developmental neurobiology that actually the nerves, as they're developing, need electrical targets to help guide them. So we may be giving them the targets from below here. It may be, we know that controlling certain muscle groups, there are these mysterious alternative pathways there, and maybe one of those alternative pathways is the one which is surviving here, and over time he's able to sort of remodel. It wouldn't be a sensory pathway, it'd still be a motor descending pathway, but one that's not well used. And then there's the last hypothesis, we don't know. And so, yeah, and so right now we're thinking about what's going to be the animal model. We don't know the animal model because it's pretty clear that the volition and intent is important to this thing, and getting that in a rat is pretty hard.
So he knows he's doing it voluntarily, but he can't indicate anything about how he's doing it.
No, and especially it was very interesting. So right before starting the voluntary movements, he started reporting these sparking feelings right around the level of his lesion, and these sort of also just pain jolts, not painful pain, but notices. And I saw right before he started making his voluntary movements without the thing, we were at a meeting together, and I was talking with him. He goes, "You know what? This week I feel like I'm much better connected to my body. I just feel that way." And then 5 days later, he started reporting these voluntary movements. Okay, so now I'm going out on a limb, and my professional colleagues are going to hammer me for this. So the question is this repeatable? And so I can't say too much because this data is not published yet. It's not been peer reviewed. We've implanted a second patient. He was a 24-year-old. I didn't mention that Rob was motor complete. He had a little sensation in his toes. We know there wasn't cord there, so undoubtedly we're taking advantage of it. This next patient was an Asia A, which he was both motor and sensory incomplete. We hope to report the data later this year. All I can tell you is he's done everything Rob's done in a year and 2 months, except the autonomic part. We haven't studied that yet. And so he covered voluntary movements. He's standing up unaided. And so we don't know with Rob is maybe just because he never thought to do it, that maybe you could have done it earlier too. We don't know. We're implanting our third patient in 4 weeks, and we have government approval to implant 2 more after that. And we haven't decided what we're going to do with those 2 yet, whether we want to go older in age, longer time injury, more incomplete injury, we don't know. I've used up a lot of time, and so I didn't even get the injury part. So let me just briefly. All right, I got to the rats, the humans, the micro devices, and so let me tell you that. Let me just give you a quick whirlwind tour of the engineering side. And so, in addition to just developing some of the basic technology, my particular task right now is to figure out what are the optimal stimuli that we should apply. So we can now generate technology which is arbitrarily complex. So here's some arrays that ties up. It says 250 electrodes. We can build thousands of electrodes. That's not the problem. So now the question is, what's the right pattern? And because the space over which possible patterns are, when you consider time variations, coupling and phasing between electrodes, it's just enormous. And so we're taking 2 approaches to that. One approach is a modeling approach. So I'm doing some very extensive modeling of the whole epidural stimulation process, actually how the electric fields penetrate into the nerve tissue, and also machine learning approach. This approach says, as an engineer, right, I want to model the system. I don't have Newton's laws, but let me figure out the best model I have. And then the other one is, the model is just never going to be good. And every patient's going to be different. So let's treat it as a black box and just sort of see, can we actually learn the stimuli? So I have 1 grad student working on each one. So they're in a competition. So let me just sort of jump ahead. So what we do on the modeling side is this is our first attempt. So what we do is we build sort of 3-dimensional called volumetric models. We're not the first people to build these kinds of models. And so we model the major tissue components, the gray matter, the white matter, the cerebrospinal fluid, epidural fat, the tissues, the bone, those kinds of things. We then sort of place various geometries of electrodes arrays on there. We then use EM equations to sort of solve the entire sort of electrostatic field. We make some approximations, and so doing that, we can then we sort of mesh the model up, and then we use sort of standard EM solver techniques to kind of solve for the distributions. So what we can do then is solve for sort of all of the distributions of the currents. So here we actually have a positive electrode and a negative electrode on one side of the cord, going down the cord, and this is sort of how the currents are distributed. The currents actually go very far here because of the cerebrospinal fluid. It's highly conductive, and so it will carry current for a long way. And then also we could solve for what are the sort of voltage distributions on this. And so we started with this, and what we then sort of did is, once you figure out how the electric fields penetrate, that actually doesn't tell you whether a neuron will be excited in there or facilitated in there. Because it then depends upon what is the neuron's diameter, how is it orate with respect to the field, and then actually what is curvature. It turns out it's the second derivative of the geometry of the neuron's bundle. It plays a key role in whether it gets excited or not. And so then what you have to do, and we're not done yet, is you actually have to sort of build neural bundles in all the key areas you want to test. And so the first one, according to your question, I don't know your name, I'm sorry, is our first hypothesis is that dorsal roots are playing an important role, because we know the sensory information coming in is key to this whole mechanism. And so we wanted to see, are the dorsal roots, which is where the sensory information comes into the spinal cord, being facilitated or not? And because we're looking for it there, yes, it's facilitated. And that's what I can tell you right now. The thing which we recognize, this is the state of the art in this sort of field. Everyone uses these cartoon models. But we found actually that these models are very sensitive to the geometric geometry that's happening. And so what we're doing now is actually trying to build a very detailed three-dimensional models of the level stable spinal cord of the rat. And so we're doing two things. So we're taking the best rat atlases that are out there, and undergrads laboriously hand trace these things, enter them in a computer, and they basically extruded three-dimensional model through all of the spinal cord atlases, as well as all the lamina, all the geometry there. But the problem is these atlases, they don't care about the cerebrospinal fluid or the dorsal roots. It doesn't interest them, but for us, it's key. So we started then taking rats and putting them in really high-string magnets. So we first used a 7 Tesla magnet, and we couldn't get enough detail in the core. We could figure out where the dorsal roots are. And so then we have a very high-string 12 Tesla magnet at Caltech. The bore is very small, so we actually have to chop out the spinal cord and stick it in there. And so we've been also developing, for those of you out there who know about these level set methods, new level set methods to sort of segment out all the bones and all of the neural tissue. And then what we're working on right now then is trying to register these atlases and these MRIs. So we have both detailed geometry as well as the anatomical overlay of what's known about the different neural pathways in sort of each area. And it's very laborious, but it's pretty vital that we think. And what's that? Well, and then we plan to put these all on the web so that people can use them. And so we're doing the same thing for the human as well. Unfortunately, we don't actually have great data. So if anyone here has a 3 or 7 Tesla MRI scan of a lower sacral spinal cord, let me know. I want to talk to you because we really need one. This is just standard grade 1.5 Tesla MRI imaging. So we've reconstructed the detail of the human spinal cord for this data as well. So we're almost out of time, so I'm going to just, I don't have time to go through the detail. And I said we're developing a variety of machine learning techniques. And then also, I don't have the slide in here. Oh well. I was going to show you some of the new robots we're building. So we're actually building sort of mechanical bronching bulls for rats, so that we can basically stimulate the rat posture and test the rat posture. So sort of advance our knowledge of actually the hospital control mechanisms in rats, and then hope someday in humans. So let me just wrap up with this slide. So I want to strongly suggest 2 things. One is, again, I'm the messenger. It's a big team. This isn't all my work. These are terrific people, and it's been great to work with them. None of us believe this is the final solution. This is just a small step. But as I said before, I think it's kind of naive to think that stem cells are going to get up and walk away, and we feel that this technology could play a role in the future of that technology. What is also clear to me, which is great as an engineer, because it's like the full employment act for me, is that in the future, as the neuroscience advances, it becomes more of an engineering problem and challenge. And so the future solutions are going to use microdevices, algorithms, tissue engineering approaches. We're not doing those right now. We're thinking about them. The modeling I'm talking about to give us greater clarity of how the mechanism goes. And above all, we've learned that the neuroplasticity is the key. You want to use biology. I think all the people are trying to bypass biology by giving exoskeletons and the other stuff. It's just not the way to go. But I'm biased. So again, we were very grateful, of course, for funding, and also the Pasadena Reeve Foundation that came in and promised to support all of our human studies going forward. And so we're really grateful for that. And again, I want to stress I have some great collaborators. So I'm happy to take questions. Yes?
It's kind of compressive injury that we saw. Are there issues of sample pain that might be made worse by it?
That's a good question, and we don't have enough data to tell you. So certainly many paralyzed people do report and have chronic sort of phantom pain problems. And it's not an area that I know in detail. My colleagues can tell you better than that.
Maybe it was made worse.
All I can tell you is with Rob, He didn't have the phantom pain, so we didn't experience it with him, and it didn't change any of the pain feelings whatsoever. And in fact, the only thing it's done is he tells a funny story. So he's going in to get a shot, a vaccination shot, and the doctor said, "This is going to hurt," and he goes, "Oh no, you're paralyzed." And so he gave him the shot, and he choked off the table because he actually started recovering, feeling these kinds of things. And so he started to get regular pain sensations back. They're not the normal pain sensations. There is some sort of dullness, and obviously not sort of normal sensation. But in the second patient did not have any phantom pain either, and has not reported anything so far. But we only have that to N of 2. That's all I can tell you.
So, but the current spread does not induce any kind of pain during the stimulation?
No.
I guess if far down enough, it didn't indeed.
Yep. Yes.
So did the second patient also get the 1 year of training without?
And the third patient just finished up training this week, so to get ready for the implant. Yes.
Were there raised connected to the neurons?
No, actually they're in this epidural space, so they're right outside the dura, so they're as close to the neurons as you can get without going inside that protective sheath. And so they sit right there on the surface, but they're still, depending on whether you're in the rat or the human, anywhere from 500 microns to a millimeter or so away from the majority of the nerves. And what our models tell us is that one of the reasons the dorsal roots get hit up is because as they come in, there's a ton of cerebrospinal fluid that goes around there, and so it tends to conduct the electric fields around there, and so that's why we believe there's a large effect there. This is only anecdotal, and I wish I had more to support this, but from everything we can tell, it looks like we're also heating up some of the interneurons that are kind of closer to the center of the cord, below the peripheral tract, but it's only based on observations that we have, and there may be other mechanisms which support that. So that's one thing I'm trying to do in the modeling right now is to sort of get a detailed study of which parts of the cord are really affecting, or at least we have a high probability of affecting. Yeah, Ben.
How did you pick the patterns for,
Trial and error.
Trial and error. Okay.
Trial and error. And it wasn't clearly trial and error. So Yuri Gerasimenko, right here. So in Russia, they can do things we can't do here. And so he had experience of doing epidural stimulation in humans, but it was sort of single wires. And so from some of these single wire studies, and also Vienna, there's a group there that's done them, and Yuri's group, and also in the rat models, we knew roughly where to be. And actually, Susie and the neurosurgeon, Jonathan Hodes, went through a very extensive sort of study and analysis before the implant to figure out, when they applied different stimuli, what should they see in the surgery room. So when they actually put it in, Jonathan was amazing. He hit it almost dead on. But then we actually stimulated him. It's actually, I was there in the surgery, and he was jumping on the table, as we were doing things. And so we kept adjusting it until we sort of felt like we had the best sort of compromised location. And on the second surgery, we don't fully understand. There's a small asymmetry there. So when the array got put in, the tip of it comes right. There's stainless steel back electrodes covered with platinum. And they're in a sort of silicone matrix, and so when they got put in there, it got bent a little bit, and so it's something we're dealing with right now. Okay. Yes?
Beyond the geometric patterns, what about the frequency stimulation? You mentioned that the stimulator you have were shifted towards the high side instead of the low.
So for stepping, we've just found that first you want to actually move the principal location of the site up the cord and go to a higher frequency. For posture control, you want to lower the frequency and go down to the lower place. Why that is, I don't know. That's something I'm trying to address in the modeling. I'm not sure I can actually do it. The other thing we know from our animal studies and actually from different experiments with Rob is that actually really what you want is different voltages at different parts of the cords and different frequencies at different parts of the cords. The technology just doesn't allow us to do it yet. And so right before I came here, I was in New York for a variety of reasons. The one thing we're doing is we're talking with the Christopher Dana Reeves Foundation to try to raise the money so we can actually build the stimulator allowance to do the flex that they want and get it through the point of the FDA approval process. When you sit down and pencil out the numbers, it's an enormous budget. And so we're going to be limited by how quickly we can raise money.
If you were able to stimulate inside that sheath, would you expect a better result, or is there some coupling with the fluid that you think is actually helping out?
I'm not sure what you mean by better, because in fact, I'm not trying to be coy with you. Certainly one of the things that I'm frustrated as an engineer, I talk to the sort of physiologists and the therapists, and I say, okay, what's the best locomotion? How do I quantify best locomotion? And they're like, we don't know. You know, we know it when we see it, but we can't necessarily give you a formula which says, you know, here's how you sort of compute better. So it's not always clear what better means. Certainly, you know her, Mouchouar. I don't know her very well. She's done some brilliant work where they've actually done intraspinal stimulation, and so what they're able to do is, yeah, okay. And so what they're able to do is different things than we can do. So they can actually hit up very specific pathways, very specific sensory inputs, and so we have a very crude hammer. And I believe in the long run, the things that she's doing, plus things we're doing, plus tissue engineering, plus many other things will be the ultimate solution. It's not going to be one silver bullet that's going to do this. And because every patient's injury is very different also, it needs a whole different approach.
Well, the question then is also, do those electrodes move?
That's a good question. And so there are reports in the background literature for which they're normally used that there's issues with the moving. And so in fact, actually, Medtronic is coming out next year with a new device, and it's fancy marketing called the sensor. And so it has an accelerometer, and so what happens is as you sit up and sit down and lie in bed, it can tell what posture you are and actually adjust the field, because they know in the different postures they raise a little bit. And it isn't necessarily that the ray itself is sliding in there. What we do know from lots of studies is once the ray is put in there, and if you have the right surgical procedure, it will sort of scar in, and a lot of collagenous tissue will hold it there. But the cord itself moves, as you know, inside the spinal column. So it does move. And so our feeling is by doing this high density epidural stimulation, you give yourself lots of electrodes to play with. If you're willing to deal with complexity, the thing you buy then is both tailoring to each patient and hopefully overcoming these effects. If they do show up, then you can sort of shift the field around. But it adds a whole other layer of complexity that we prefer to avoid if we can. Yes?
So do you know if your electrodes affect the brain, or is it just meant to the circuitry that's apart from the brain?
That's a very good question, because we first initially thought that when you see these complete spinal cords, we knew, everyone's known for a long time. We don't know actually how much is left in the cord after a major injury. The difficulty right now is the MRI technology is just not good enough for us to get down at the detailed scale to see exactly which parts of the cords are potentially intact and which ones aren't. And so, our hypothesis going in was we were hitting up that CBG circuitry and there was, total brain disconnect. Obviously, the fact that they're making some voluntary movements means that there's a connection there. And so it is one of the sort of the distant hypotheses that there actually may be some remodeling in the cortex going on here. That would be amazing and wonderful if it were true. And unfortunately, we can't study it. The reason we can't study it is after we implant these guys, we can't go in an MRI. So we just don't know. And so, and I'm not the animal physiologist, Reggie is, and so he's racking his brain right now trying to figure out what's the animal model that we can study this in. Yes?
I think did you say that regeneration helps in this process and stimulation helps in regeneration?
No, it's a hypothesis we have, and so we have absolutely no evidence whatsoever that that's true. But it's a logical hypothesis that we'd like to test sometime in the future, but we're far from that. Yes. Let me say one thing. I know some of you probably have places to go, to go to, homework to do, those kinds of things. Feel free to leave, but I'm happy to stay as long as necessary. I'm staying here tonight. I'm not going anywhere. So if you have any questions, I'm happy to stay.